Remainder estimation for power series. When we truncate the Taylor series, we split it into two parts. We have the part that approximates the function, or Taylor approximation, and then we also have the leftover part, which we're going to call the remainder term. If we look at the Taylor expansion here, we have our Taylor expansion, and where we stop, that's going to be our Taylor approximation. This leftover term, which we're going to call the remainder term, which we noted as Rn of x, that will get us to the exact value of f of x if we let it run to infinity. So the formula then for Rn of x is going to be from the n plus 1 term. So if we chop it off at n, the green part, our Taylor approximation stops at n. We go to the next term, n plus 1, and then we can run that to infinity, and that will calculate essentially the error. The problem with this term is that it does still rely on infinity, and we can't actually calculate it because we won't have infinite number of terms. Now, the Rn of x can be found without using infinite terms. And it's going to be based on the n plus 1 term of the series. This Rn of x looks like this. So the formula is essentially the same formula, except now instead of using the center as the next term, so notice we usually have the center, this usually is c here. Instead, we're going to choose to find the derivative at some point b. Now, the problem is we can't actually we don't necessarily know where it is, but we know it exists, and we know the bounds of where it exists. So we have this theory that says, this is the Lagrange form of the error term. We have this theory that says that the remainder term can be calculated using the n plus 1 term of the expansion and some unknown point b, and that will actually calculate the exact error. Now, unfortunately, that point b is a theoretical point. It's not a theoretical point in that it does exist, but we can't necessarily find that point. But because we can bound b between the center c, and we know that point b is somewhere between the center and the point that we're approximating, since we can bound b, we can actually bound our error based on that. So there's a theorem and a theorem that says that b exists to calculate the exact error. We can't necessarily find it, but because point b is bounded between c and x, we're going to use that to bound our error. Now, as a side note, that point b is actually related to the mean value theorem. In fact, this is the mean value theorem not for linear approximation, but for an nth degree approximation. And in the linear form, the mean value theorem looks like this. So we know that if we want to get from point C, the center, to the point X that we're approximating, there is a slope that exists that is at somewhere between C and X. We don't necessarily know where that point B is, but we know that slope must exist where it's parallel to the slope that will get us from point C, our center, to the point X that we're approximating. So this Rn of x is actually related to mean value theorem. In fact, it is the nth degree of the mean value theorem, where the mean value theorem is of degree 1. It's a linear approximation. The Lagrange form of the error term is an nth degree approximation of the same thing. If you're interested in finding out more about the Lagrange form of the error term and how it relates to mean value theorem, there will be a link in the video somewhere up here.